So here we have a problem about a car going around a banked turn. So what forces are going to be acting on this car? Let's just draw a quick free body diagram off to the side from the same point of view. So this is the car from behind. We know there's going to be a force of gravity, right? We know there's going to be a normal force perpendicular to the slope. And what other forces are we going to have? Well, we're also going to have a force of friction, right? If this car is going along the road, it's going along a curve that's sort of banking to the left, right? So it's sort of, if you were to extend this forward, if I was to make this into like a 3D drawing, let's try, right? So this is like the bank of the road as the car goes around, and it's going to sort of follow this banked path around there. So if that's the case, what's keeping that car on the road? What's keeping the car from sort of sliding off the road to the right? In other words, what's providing the centripetal force that the car needs to follow this circular path? And the answer is friction, right? What direction is the friction going to be? Well, again, it's preventing the car from sort of sliding off the road to the right, and it's along the surface of the road. So what we can say is that it's actually along the direction of the road, right? Let's ignore the friction in the path of the car, like in the direction of the car, and let's just look at the friction that the tires have with the road. So this is like here and here. The tires basically need to be pulling the car this way so that it follows that corner, right? So these are all the forces. Now we can calculate the gravitational force, but the normal force and the force of friction are a little bit more complicated. Do we have enough information to figure those out? Well, the new thing that we need to do in this question is to look at the centripetal force. So remember, any object following a circular path needs to be accelerated in a specific way using a centripetal force. So the thing to think about for this car is that the path that it's following is a circle, and what direction is that circle in? Well, looking at it from above, if this is the track, right, and the car is over here, right, and it's following this, the circle, the center of the circle is going to be to the left of the car like that, right? Now, you might be tempted to think that the centripetal force, the direction of it, is down along the road, but the path of the car doesn't follow this circle that goes down along the road. The path of the circle, or the car, is around a horizontal curve, right? So the actual motion tells us the centripetal force needs to be to the left, directly to the left, horizontally, because that's the direction of the circle. And we also know that it's 600 meters, right? Now, the thing to keep in mind is that the centripetal force is the net force. So we can't draw that on the same free body diagram, but we can draw it on a separate free body diagram. So this is the net force or the centripetal force. And we can calculate that as well. So what we know is that these three forces here need to combine to give us this centripetal net force. So that's what we're going to do in this question. So let's start off. We can calculate a few things from the beginning. We can calculate the gravitational force on the car, which is 1,800 times 9.81. So that's going to come out to 17,658 newtons. And the other one that we can easily calculate is the centripetal force, right? Because we know the centripetal force is going to be mv squared over r. So if we do that calculation, remember to convert the kilometers per hour to meters per second. And if you do that, you should get 5208 newtons. So that means this net force to the left has got to be 5208 newtons, right? Now, the key is, how do we get these three, or the question is, how do we get these three forces to add up to this? Well, first of all, we have some forces acting on like these angles, and then some forces acting like directly down or directly to the left. So we should come up with a convention that makes sense. Because of the fact that we're used to using, on a slope, we're used to using sort of the length of the slope as our x direction, we're going to continue to do that here. So I'm actually going to make x, our positive x direction, down the slope, and I'm going to make our y direction perpendicular from the slope. So the force of friction and the normal force are the things that are in those directions. This gravitational force we'll need to divide up into components, and the net force we can actually divide up into components. So that's our next step, is we're going to divide up all the forces into components in those two directions. So first of all, we know how to do the gravity, how to change that into components. I'm actually just going to draw another free body diagram here, but instead of with the total gravitational force, I'm going to do it with the components. So here we have a normal force, which we still don't know the value of. The friction force, which we still don't know the value of. But the gravity we can divide up to its x and its y components. So I'm going to do those in blue just to separate it. This component here, right, which would be this component here, is going to be our m times g times cos of the angle of the slope. So what that's going to come out to, if our mass is, what was our mass? 1800 times 9.81 times cos of the slope, which is 8 degrees. So what that's going to come out to is a pretty big number. That comes out to 17,486 newtons. And we also have our y component, sorry, our x component, right? Which is going to be like that, which I'm going to draw like that. It doesn't really matter where I put it. I'm going to put it there so it's sort of clearly in the same direction as the F force of friction. So this is going to be mg sine theta. So that value is going to be 9.81 times 1800 times sine of 8 degrees, which is 2458 newtons. Okay? So that's our x component there. So we still have these two unknown forces here. You might be tempted to make the normal force equal to this gravitational force here, but remember, the normal force, or the net force, is not zero necessarily. It might be, but we don't know. Remember, we have to try to find out how to make this force, how to make all these forces equal this force. So, looking at the second free body diagram, how do we make components of this force over here? Well, we can do the same thing. Remember, this is going to have components in the x direction, right? And components in the y direction. Now, remember, the slope is 8 degrees, so the 8 degrees is in here, right? Because it's just the same as the slope. So, in other words, this side here is going to be our centripetal force times cos of 8 degrees, right? Because it's the cosine, it's the close side. And the y component of the centripetal force is going to be our centripetal force times sine of 8 degrees. Right? So those are our two components of our force. So let's actually put the values of those over here. We know we're going to have this component and this component. So the x component, if we calculate it, well, our centripetal force was what? 5208. So it's going to be 5208 cos 8 degrees. So our x component is 5157. And our y component is going to be the same thing, but sine of 8 degrees, which is 725. I'm just rounding these all to newtons, to the closest newton, because that keeps at least 3 significant figures for each one. So hopefully you can sort of see where we're going with this. Remember, this is the net force. So this is what we're trying to achieve by summing up these forces. So in other words, in the x direction, we want the sum of the forces to be 51,057 newtons. Right now, we have two forces here. We know one of them. Could we find this one? I think we could. In the y direction, we know we have two forces, this one and this one, and we want those to sum up to 725 in the y direction. So to make this a little more formal, why don't we name some stuff? We're going to name this force here F net in the y direction, and we'll name this F net in the x direction. So let's look at those two separately. So in the x direction, we know F net in the x direction is going to equal, well, we have two forces here, right? So we know it's going to equal this 25, or I guess what this was the force of gravity in the x direction, right? This force here. And then the force of friction. Remember, we said the positive x is down the ramp. And then we said in the y direction, F net y, we have the y component of the gravity, so FGY, which is in the negative direction, so we'll call it negative FGY, plus the normal force, right? Because the normal force is in the positive direction. So let's plug in some values and see what we can do. Well, we know the F net in the x direction is 5157 newtons. We know the FG in the x direction is 2458. And we want to solve for the force of friction. We can solve for the force of friction. All we need to do is subtract, and it comes out to, the force of friction comes out to 5157 minus 2458, 2699 newtons. There we go. So the force of friction, in order to keep the car on the road, needs to be that much, 2699 newtons, so about 2700 newtons. And for the y direction, F net y, this should be F net y, is 725 newtons is equal to the g in the y direction, Fg in the y direction is 17,486 plus the normal force, which we don't know. We can find the normal force by adding those two together. So 17,486 plus 725, which is, the normal force has got to be 18,211. So we have our two answers here. One thing to notice is that the normal force is not equal to the gravitational force. They're not equal and opposite each other here. And part of the reason is because the car is going around the circle. There is that centripetal force, which pushes down. Basically, the car is pushing down more on the road, or the road is pushing up more on the car because of that centripetal force. So there we go. The second part of the question asks, what force is required to keep the car going around the corner, and what must be the coefficient of friction be? So to keep the car going around the corner, well, we know the friction force needs to be 2699 newtons, so about 2700 newtons. Let's actually, you know what, let's put these in less significant figures. 2 significant figures works for this question. 2700 newtons, and the normal force is about 18,000 newtons, right? So the normal force, the force of friction is that force that needs to keep the car going around the corner. And if the tires couldn't provide this force, then that's when the car would sort of spin out or go off the edge of the road. The last question says, what must the coefficient of friction be? Well, we know the coefficient of friction is defined as the force of friction, the ratio between the force of friction and the normal force, right? So we can just calculate it. 2699, I'm going back to my ones that were unrounded, 18,211 newtons and newtons. The newtons cancel out to give us the unitless coefficient, which is 2699 divided by 18,211. Rounding to 2 significant figures, it is 0.14. It's actually a very low friction coefficient that's required here. So by the way, this is the friction coefficient that's required to provide that. But in reality, we just want to have a coefficient of friction that's higher than that, so we know that the car doesn't skid out. Okay? One more question I have for you. Is this a kinetic or static coefficient of friction? Think about it. Remember, a kinetic force of friction, or kinetic coefficient of friction, is when two surfaces are sliding across each other. And a static coefficient of friction is when two objects are in contact with each other, but they're not moving relative to each other. So I want you to think about that. I'm not going to answer it here. The last question I have for you. I want you to think about what would happen if I change this 8-degree bank. What would happen if I change it to a 5-degree bank or a 10-degree bank? So if I increased or decreased the bank, what do you think would happen to the forces involved? Would the force of friction increase or decrease? Would the normal force increase or decrease? I want you to think about that. Maybe try calculating it to check your work, to see what happens in those cases. All right? There you go.